Ramis, welcome to the channel. I'm excited to have you.
Great. Thanks, Dimitri. I'm glad to be here.
So, why don't you start off with just a quick introduction of who you are a little bit? I'm really excited to chat with you. I don't get to talk to people that work in the quantum space very often.
All right. Yeah, sure. Thanks for having me. Um, well, I've gotten very interested in finance, as you know, in the last few years, like along what we discussed before. But my background has mainly been in hard sciences. So I did let me just start from undergrad onwards,
Yeah.
because, going back too far might be beyond the scope. But yeah, so I did my undergrad at Cornell in applied and engineering physics. And then I spent about 3 years at ETH Zurich, so in Switzerland, working in neuroscience, what you might call early AI, as well as mathematical physics.
Okay.
Then I was briefly a PhD student there in mathematical physics, but I also got admitted and came to MIT in Boston, Cambridge, and worked with Peter Shor, who was my supervisor. So Peter Shor is like one of the maybe most famous name in quantum computing. So I started working on quantum computing that way. It was kind of randomly I got into the field because I just liked Peter, and I guess it was reciprocated. So we just started talking, and I was like, well, we could do some interesting science together, and that's how I got into the field. And after that, I did a bit of postdocs around. So at MIT, University of Chicago, I worked with Leo Kadanoff in statistical physics. Then I was a Goldstein Fellow, which is some fancy postdoc at IBM Research in Yorktown Heights, New York. Soon after, I became a permanent research staff member at IBM, all in quantum computing. After a few years, I was recruited by Google, and I went there in quantum AI, worked as a researcher in quantum AI. And most recently, I've been doing some finance on my own, non-quantum finance, I was very curious about it. So I built pipelines, end to end, and developed strategies in finance, which is great. And I've been part of a startup that deals with post-quantum cryptography. Now, post-quantum cryptography is about, I can say a little bit more about it. So quantum computers, one application of them is that they can break cryptography as we have it now,
Hmm.
the so-called RSA. And they can also attack Bitcoin wallets. So the question is, what kind of cryptographic system do we need to put in place to be resilient despite quantum computers? And that's why it's called post-quantum cryptography. And in the last few years, I've become very interested in beyond quantum computational advantage, especially with applications towards finance. And I can say a little bit more to your audience if you want. I can give a primer to quantum computing. I think the interplay of quantum and finance might be interesting in the next few years.
Yeah, this has been a focus I think I've been casually looking at, and I feel like it's been completely washed out with the AI trend and the hype lately. But yeah, I'd love to get into the details of like what is quantum computing. I know a lot of people in finance we hear it as like this buzzword, but we don't often have the time to dig into it. Do you want to cover a little bit like what is quantum computing and how is it different from traditional methods?
Absolutely. So, what do you say I show a few slides? Okay, so I'm going to tell you about quantum information, which includes quantum computation, but also more. So, quantum information, computation, and beyond. So, quantum physics. Okay, so I'm Ramis Movassagh, and I'm on X as well as LinkedIn, and I have a website on which I have a blog. I talk about my work. I have to make some new posts, but there are few stuff there already. So classical computing means every sort of computing you've heard about. Your laptop, the supercomputers in Summit. If somebody tells you about neuromorphic computing, um, all of these at the end of the day are classical in the sense that they work with zero ones. And to put it technically, you can reduce them to a Turing machine computation. Turing machine is some computational machine Alan Turing in the 1930s, um, came up with, which is like a universal model of computation. And all computation can be reduced with small overhead. I'm intentionally not telling you polynomial overhead because I want it to be accessible, but with some overhead that's reasonable to a Turing machine. But if you look at the Turing machine, it's a classical object. So everything you've heard about is like Turing machine computable. But quantum physics is like fundamentally different, and one can talk about its applications, in particular applications into computation and technologies. So let me say a little bit about classical versus quantum. The key distinction is that classical physics is deterministic, which means, like, for example, you've seen that people can send rocket ships all the way to like very distant comets that are like 2.5 kilometers in diameter. This happened like a few years ago, like maybe 10 years ago, with the European Space Station. It just shows how much control we have over simulation of how the rocket ship could go and like land on something with such small gravitational force, despite all other forces around. It turns out in quantum, and we can do so deterministically. I think I'm getting ahead of myself a little bit. But the way classical physics works is that if I want to, for example, calculate throwing a tennis ball and I want to see where it's going to hit, all I need is that where the tennis ball is right now. So that gives me, so that's the initial position. And that requires an X, Y, and Z coordinate, right? Like where it is.
Yeah.
X, right? X, Y, and Z coordinate. And then what I need is like how it's moving right now. Also, velocity by which I throw it will affect where it's going to hit the ground. So there's an X, Y, and Z velocity components, right? Like, for example, I'm going to throw it in this direction with certain magnitude. Given these 6 data points, so 3 position, 3 velocity, and the fact that there's a gravitational force, we know the gravitational force, I can with certainty predict where it's going to hit the floor.
Mm-hmm.
And that's because F equals ma, and a is x double dot, which means twice derivative, and you can integrate it twice. And you need initial conditions to uniquely specify the constants of integration, and that is position and velocities.
Makes sense. Okay.
Yeah. And then you can, with that, just predict where it's going to go in the future. And if you catch it somewhere in space, you can tell where it came from. You can integrate backwards even, the full trajectory. It turns out when you look at very small things, so this happened, like classical physics was just so perfect in early 1900s, and people thought, physics is kind of done. And there were just these like fringe experiments that people thought, maybe the experimentalists didn't do it quite right, or that it's just like a complex classical physics that they had to figure out. But when people started being able to look at the matter in very small scale, like technology developed enough that they could look at, they could start poking at atoms and look at very small things. They saw bizarre things. They saw, for example, that like an electron doesn't just do a Kepler orbit around the nucleus as you would expect, but it jitters around. They saw that the way matter interacts with metals, like when you shine light on metals, the way matter reacts to it, the way it ejects the electrons, doesn't really add up to like the classical theories we had. They were just these fringe experiments that just seemed like at odds with what we understood. And people tried really hard to massage classical physics to explain it, but it just wouldn't work. And quantum mechanics was born. And quantum mechanics is the mechanics of very small things, at least initially was. And it's just so drastically different from classical. The whole formulation is just it's so different that even some people today complain about like, quantum mechanics may not be complete, and why probabilistic. And what we learned is that actually nature at the very fundamental deep level is not deterministic. It's probabilistic. So if I were to throw an electron, as things get larger and larger, determinism becomes more and more accurate. But if you look at very small things, and it's not a question of, like not throwing it perfectly or not being a good, or, having environmental factors. Even if you control for everything, if I were to throw an electron instead of a tennis ball, the absolute best I could do is predict various probabilities of where it might hit.
Okay.
Like it will not certainly hit, that spot, even if I do like, absolutely perfect trajectory. But, it could be like 77% there, 3% here, 1% there, etc. And it
Yeah.
just turns out that is the case. Like, it's not a question of, throwing it more precise or measuring it more precise. That's just how nature works at its very core.
Okay.
And in particular, if I specify the initial position very, very perfectly, because of what's called Heisenberg's uncertainty principle, I cannot predict how things are going to move. It's just going to, they're complementary variables. Position and momentum or velocities are at odds with each other. You make one precise, the other one becomes very varied,
Yeah.
uncertain. Now, this is physics, but quantum mechanics has been like the backbone of much of technology in 20th century. When you get an NMR, when you have lasers, your phone wouldn't work without Josephson junctions and transistors. These are all applications of quantum mechanics. And yet another application is in computation. That's where quantum computing is born.
Okay.
In particular, classically, you have bits. You've heard of them, right? Like
Yeah.
things work with 0 ones.
Yep.
So these are 4 bits, if I can count. So 0010. That could be like, a message, maybe an email that gets encoded and sent to you from me. Quantumly, what will happen is that you can have a superposition over bits. Now, let me say what that means. That means, so instead of my 4 bits, I have now, let's call them quantum bits or qubits, we call them.
Okay.
We can talk about, how you can build a qubit, but, we have qubits. And what it means is that if I have 4 qubits, they can be in a superposition, which means like if you look at them like billions and billions of times, you can get these sharp probabilities. You can just prepare it such that 11% of the time, when you look at it, you observe, you try to measure them, you get 0010. 27% of the time, when you look at it, you get 1110. 44% of the time, you get 0101. You never get something. You never get a half. You don't get like 0 half.
Yeah.
But it's just not certain that you have these like bits that are hard bits, and you compute with them. So you can actually prepare it in a superposition, sub-probabilistic superposition. And like I said, people still complain about these things. Like Einstein didn't like it. He said, this non-deterministic nature of quantum mechanics is because of hidden variable. We don't understand nature well enough. God doesn't play dice. He complained. As it turns out, as far as we can tell, God indeed does play dice. I mean, it's just really probabilistic, the nature of the fundamental nature of reality, as far as we can tell. And I could get into Bell's inequality, etc., which formalize this, the probabilistic nature. Now, this probabilistic nature can lead to some very strange phenomena that classically are absolutely absent. Like we just don't have it. Like one is entanglement.
Okay.
Now, let me explain entanglement because it like mesmerizes people, but it's actually not that complicated. So if we have, suppose you and I are co-located right now, and we have 2 quantum bits. I hold 1, you hold 1. Throughout, you should think of this as like my qubit, and this is Dimitri's qubit. Also, this is my qubit, the first one. This is Dimitri's qubit, the second one. Second one is yours, first one is mine, by, arbitrarily choice. You and I can interact our qubits and put them in the following state, which means half of the time, if people were to look at, or you and I were to look at some objective looking at the 2 qubits, half of the time we would get 0, 0. Half of the time we would get 1, 1. That's just the state we prepared.
Okay.
Now, the reason this is strange is that suppose now we're in this state. I hold my qubit. You go to a distant galaxy. Or you go where you are right now, right? Now, if I look at mine, I can only get 0 or 1, right? Like I cannot get something in between. If I happen to get 1, I'm looking at it, I get 1, then this state is selected. I told you, like whenever you look, one of them is selected.
Yeah.
Then this is selected. They also call it collapse of the wave function. I don't like that terminology, but it collapses to this particular string, bit string.
Yeah.
You know what this says is that if I get 1, then yours must also be 1.
Okay.
Yes. So by just measuring it at my end, now if you're in a very distant galaxy, forces in nature are a function of distance.
Mm-hmm.
go very, very far away, you and I are not even interacting. Like I'm not sending you any signals. But by just measuring my end, something happens to your qubit. Your qubit is no longer in a superposition of 0, 1. It becomes certainly 1. And that's very weird.
Yeah. Yeah, it's an
That's
odd
very,
concept.
yeah, that's very weird. So that's entanglement. This indeed is a Bell state, they call it,
What
named
is
after.
this applied to in physics? Is it electrons or is there like a specific thing, like an example they've tested to prove this?
Yeah, that's a great question. So there are many models of a qubit. It could be an electron in state up or down.
Okay.
So you and I can interact our electrons such that they're both like this. Or half of the time is like this, half of the time is like this. That could be an example. You could also encode these into like photon states, polarization this way versus this way. Or in modern times, when we do quantum computation, there are various models. People use ions, trapped atoms, and certain states of atoms. Or the traditional model of quantum computation, the superconducting qubits, which this year won the Nobel Prize. So there are many models for a qubit.
Okay.
In this particular example, usually people, like for quantum communication or things, people use photons. And yeah, so now what is quantum computation? Well, if you start with classically, you have bits that you start with, you send it through a computer, which could be sending an email or doing some computation, and you get out some bit strings that you interpret.
Okay.
Quantumly, you can start from this superposition, which is like some, probabilistic superposition. You send it through a quantum computer, which implements a quantum algorithm, and this is where the genius lies. Like coming up with good quantum algorithms, that do meaningful things is actually very hard. The misconception is that when you have a quantum computer, everything gets sped up.
So you just throw stuff in, right?
Yeah, that's right. That's right. You just put a Q and everything is just like on a steroid. And that's just not the case. So you send it through, and the way to conceptualize this is that the quantum computer looks at all these possibilities, and if the algorithm is very good, it interferes these possibilities in such a way that at the end, you get a result. If the algorithm is good, like say Shor's factoring algorithm, with high probability, you'll end up getting the answer that's desired, say the factors or whatever it is that you want to compute, because the algorithm was clever to use these superpositions. And with a low probability, you'll get garbage. By garbage, I mean, the other possibilities that are not desired.
Okay.
Now, this may sound kind of stupid. You're like, well, I gave up like something with certainty I could do, and now I get something with high probability, and I also get some garbage I got to deal with. But now imagine if this high probability answer is obtained, say, I don't know, 99% of the time.
Okay.
With the difference that this computation is much, much, much faster than this computation. And when I say much faster, for example, in factoring, there are things you could do in 2.5, 3 hours that would take celestial times if you were to do it on the left because of some exponential separation. For large numbers, it's just going to be so expensive to do it classically. Well, if it's going to take, I don't know, like 10 trillion times, or I said, let me be safe, 10 billion times,
Yeah. Okay.
10 billion seconds or something, and this one I can do in like 2 hours, then, well, I just do it in 2 hours and I repeat it 10 times, 100 times, whatever I like. And when I see this, according to probabilities I want, I know this is the answer.
Okay. That makes sense.
Yeah, and in certain cases, you can actually verify the answer. Like with factoring, if it gives you the factors, well, you just multiply it and check that it was the initial. It's called self-correcting initial thing. So you don't even have to run it multiple times. So yes, you give up determinism and certainty, but for certain tasks, and I emphasize for certain tasks, not everything, you might get some awesome speed ups,
Okay.
which then you can utilize. Another myth about quantum computing is that it runs everything in parallel and just selects the answer that's correct. That's also not quite true, because that would be great, but that's just too much. As you can see here, like if you were coming up with a good quantum algorithm that interferes things just to give you high probability weight on the answer you want, is just very difficult.
Yeah. That makes sense.
And computer doesn't know what to select. It just gives you some outputs.
I've seen the analogy of looking at like analog computing versus I guess digital. So it was
Yeah.
very odd for me to look at that historically and realize like analog is very like fuzzy and there's always a lot of error to it. And I think about like watching TV back in the olden days, you know, with like static within the TV.
Mm.
Can you explain a little bit, I guess, to some of the listeners as well on like the difference between digital and analog and how I think like doesn't quantum computing it has like, essentially that margin of error. Like there's a little bit of like that static because it's not necessarily split into like a digital binary of 0 1.
One major difference between analog and digital. So digital is extremely convenient for computation. It took over computation for us, right?
Yeah.
But at the end of the day, they're both classical.
Okay.
So with the analog computing, there's so if so for the viewers, analog, what Dimitri means by analog is that you have a continuous of voltage. Suppose your voltage can go from 0 to 1. In particular, it could be like 0 0.6, 0 0.7. But digital is like 0, 1, really. You have 0 or 1. Now with analog, the way it worked, like people were like, all right, if it's above 0.5, we call it 1. If it's like below 0.5, we call it 0. And this is how they digitized it, I guess, and used it. And digital age hit, and I mean, analog is not dead. It has its own interests and applications, which is like beyond my interests or knowledge, but it's still there. Like people talk about analog computing. But quantum computing is fundamentally different because I see where you're going. Like, you could think of 0.7 as like the probability 0.7 of having 1,
Yeah.
and call that 1. The one major difference here is that you can have interference in quantum computing, such that you can get, like, for 1 qubit, it may not be that much, but as you have like more and more qubits, you can put things in states where probabilities interfere destructively. You see, classically, probabilities can add. Like if you have 0.1, everything is positive.
Okay.
But quantumly, you can actually have like two things go in and have no probability of being observed here. And that's why we get these entanglement states. You can never get entanglement out of analog.
Okay. I gotcha.
So they're just new states, possibilities of interference that you can then utilize for computation.
Okay.
Quantum computing cannot be simulated with an analog computer, but you see, once you look at the probabilities, they become classical. But before you get the probabilities, you have this wave function that is complex valued. I'm getting a little bit technical, just maybe for some people.
Yeah.
So complex valued means like, it could have a phase. The phase isn't always positive like probabilities. It could be positive, it could be negative, it could even be like e to the I alpha, which is some complex number.
Okay.
These e to the I alphas can add up, when you add them, you don't get like 0 or 1, you get another e to the I beta. And when you measure, you get different probabilities, especially when you have them interfere in interesting ways.
Okay. I gotcha.
So the point of it would be that, yes, it's probabilistic, but for certain tasks, the quantum computers perform computations much, 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 much faster. And the reason for triple much is that I'm trying to get across exponential speed up.
Okay. Yeah.
2 to the x is, for small x's, is not so different from x squared or x to the 10, but as x gets large, 2 to 1,000 is very different than 1,000, squared, or 1,000
Right.
power 5 or something. So some applications are in like factoring numbers, which is what RSA and cryptography based on. Simulation of quantum matter, like very small things, like very small molecules or atoms. They're very expensive to calculate on normal supercomputers. But if you have something that's made up of quantum, I mean, this was Feynman's dream. It's actually not a bad paper if you want to read it, in 1981. So you can like simulate quantum stuff with a small overhead, because they're similarly weird.
Okay.
So, you don't need to do this extra work to reduce it to classical. For searching data sets, quantumly, you can do things with a moderate speed up, like quadratic, we say. Something that takes 1,000 steps, say 1,000,000 steps, would take 1,000 steps quantumly. There's a quadratic speed up.
Okay.
But there are advantages to quantum technologies beyond computation, which I've gotten very interested in. For example, you can do things because of this entanglement, for example, non-locality. You can do quantum. You can gain quantum computational advantages in cryptography and other areas, which I think may be interesting for financial applications. I could talk about various types of quantum advantages. Do you want to hear it or?
Yeah. Let's
Okay.
dive into this.
Sure, sure. So quantum advantage is defined to be something a quantum computer or a device. It doesn't even have to be a computer. It could be a communication channel. It could be a crypto scheme. It could be whatever it is. It could be a quantum memory, like something that stores information. But if it uses quantum physics to perform a task or do something with more favorable resources than any classical, we say there's a quantum advantage.
Okay.
We have discovered a quantum advantage.
Makes sense.
And if that advantage is in time, that is like computational time in the lab, like factoring numbers that we talked about, that would be a sort of advantage. It's time complexity. In language of complexity theory, it's time complexity theoretical advantage. Like Grover's search that I told you has like quadratic speed up. There's Simon's algorithm, Shor's algorithm. Now, among time complexities, the ones that we're very interested in are the ones that give you awesome time advantages. We say exponential advantage. Because exponential, as the size of the problems become meaningfully large, really pays off. You see, right now, quantum computers are very expensive. The overheads are high. Classical computers are just so beautifully run. They're just so great. So you really need a big separation that at scale, you can do things that practically would be impossible to do classically. And we hope, factoring is one of them. Quantum simulation is one of them. Random circuit sampling, or quantum supremacy, if you may have heard of it, made a splash. It's a field of work. So these we hope are such examples. Let me say why I say we hope. So Shor's factoring algorithm, which is the crown jewel algorithm of quantum computing, and we've based crypto systems on it. We believe it's hard because we have failed to come up with classical algorithms that break it. We don't have a proof. We don't have a mathematical proof that factoring is hard. We just know that for many years, many great number theorists, scientists, etc., tried and they couldn't. They couldn't break it classically. It seems hard classically, but we don't have a proof.
Okay. Same
with most of these. Actually, Grover's search algorithm is interesting. It doesn't have an exponential speedup, but it's provably quadratically faster. That is, you can prove classically you cannot beat it.
Okay. There's more of like an experimental proof. Is that what you're saying?
No, mathematically you can prove. Mathematically, you can prove that Grover's search is like, it gives you quadratic speedup, period.
Okay. I got
It's not like, one day we're going to have a more clever search classically that is also going to give you quadratic speedup over what we know.
Okay. I gotcha.
Then there are quantum demonstrations. There are certain quantum states of matter, like topological Majorana models that I've worked on in the past, that are very hard to simulate classically. But on quantum computers, you can simulate them, probe their properties. It's called quantum simulation. And intentionally, I put it in and out of quantum advantage because some of those properties may be easy to do on a classical computer, some may be hard, and would be a point in doing them on a quantum computer.
Do we have any idea where the threshold is?
For
like traditional computing, it's like it'll double every so many years, but there has to be some sort of limit where we think like we will top out. I mean, for quantum, I know it's fairly new, but is there like an understanding or like a theory or a debate of like where we think it will stop?
Where it stops. I see. That's interesting. First, I was gonna say, Moore's law that you're referring to.
Yeah.
You double speed and half the resources, etc. Is a great thing to bring up because like how much smaller can we make things? Like as things get smaller and smaller, at some point you hit that quantum limit. You're looking at things that are small as like atoms. Well, if they're atoms and you're getting them close to each other, then it's just not gonna be bits anymore. You have to deal with the quantum effects. So that would be the limit of classical computation. There's a point beyond which like you just can't go indefinitely into zero. Like there is a point that you're gonna hit an atom, right? And that point is getting near. Like these these transistors are like very closely, tightly packed.
Okay.
So there, you cannot avoid but to deal with the quantum nature of matter because things are getting too small and too interacting. Quantumly, we're at this stage right now that, we're lucky to have like a few hundred good qubits. And when I say good qubits, means like these are qubits that you can play with for a little time before they go crazy. Because, quantum error correction is very hard. Like that, you see, classically, you can have errors. Like you want to do 0, 0, some fluctuation hits, you get 0, 1. This is an error.
Yeah.
It's called a bit flip error.
Yeah.
Then you
Yeah.
can correct it.
Yeah, I studied this a little bit. Oh, man, it's been a long time in graduate school,
Yeah.
where memory essentially corrupts. So
Mhm.
we start to lose the 0, 1 is hard coded, but then when they get, I think it's the interference of the electrons or whatever are so close, then sometimes you can have an error in there and it will flip a 0 to a 1 or a 1 to a 0.
Absolutely. Yeah. Yeah, that's right. And then, there's a whole field of, that's actually a beautiful field, mathematically beautiful field, very deep, very interesting, called error correction. It's classically a very interesting field. I mean, wonderful connections to algebraic geometry, to, coding theory, to, every area of discrete math almost. And then there's quantum error correction. So being able to correct the type of quantum errors you get. As it turns out, quantum errors are just a lot more annoying. Like not only you can have a bit flip, you can go from like 0, 0 to minus 0, 0, which is like a phase flip. Or you could have 0, 0 to like e to the I alpha 0, 0. These are things that are complex numbers that you just do not get classically. And then, the question is, can you detect it and can you correct it? So quantum error correction is just harder. And that's why like scaling quantum computation has been a little bit difficult because it's not just about having qubits, but it's about having qubits that are reliable and you can operate on them. Like put gates that, do a computation, implement the circuit. And to do this coherently, meaning like, the state is reliable at every stage of the computation, you need good gates and you need good qubits. And to preserve that goodness, you need to be able to correct the errors as you go along the computation. And that is a very challenging thing to do. So like for 100 good qubits, you might need like thousands of physical qubits to just support the computation, to get a logical qubit.
As the computations get more complex, does the error, is that become larger of a problem because you have somewhat of a compounding effect?
Absolutely.
Okay.
That is why, some famous but not always very well-informed people have resisted quantum computing. They're like, oh, it will never work because, decoherence becomes worse as you scale. And of course, we understand these things. But it is a challenge. Scaling is a challenge. It's not just like you just throw more money, you have more qubits. To be able to like get entanglement or correlations across the chip reliably and keeping it is not easy.
I guess is the field very, I guess sounds like it. Is the field very focused on like the theoretical construct of really understanding? Or is there a group of, I guess, I'll call them rogue quantum researchers where it's more or less like we're just throwing trash in and hoping something sticks? I know there are some fields currently popular, like LLMs, I
Yes.
feel like is that field where it's like we don't really care how it works, we just care that like something comes out. Is there different parts of the quantum space where there's different groups of people that are kind of looking at different perspectives, or like how is that structured?
Yeah, no, that's a great thing to bring up. One thing I like a lot about quantum computing, and I think we got lucky, is that the the fathers of this field were very rigorous people. Like Peter Shor was a mathematician, Alexei Kitaev is a mathematical physicist, Charlie Bennett wasn't a mathematician, but I've talked extensively with him at IBM. He has a very rigorous and brilliant mind. So the people who really kickstarted this field took very great care about provable advantages. Like, Peter Shor's algorithm isn't just like, hey, look, I have an algorithm, it seems to work. He
Yeah.
actually comes and proves it,
Yeah.
gets the constants, gets the scaling. He really has a quantum algorithm that in every mathematical sense is an algorithm that they can run. Whereas, you know, like as brilliant as Feynman was, if you read his paper, there's nothing provable. It's kind of like, oh, you build a computer out of quantum stuff. Hopefully, you'll do well with quantum stuff. And he does it brilliantly, you know, and, you know, you get excited by it.
Yeah, the fire charm.
Feynman charm, brilliant, you know, and of course got people excited. And there's, you know, not to, you know, discard, you know, the charisma, the importance of it, and, you know, have being the first one to say these things. But the field has this culture of, you call an algorithm, you really take an algorithm serious if it has some mathematical proof behind it and can be implemented and things have been worked out. Now, there's an aspect of the field which I think is also valuable, which investigates heuristic algorithms. You know, it's like, this thing might do better than our standard algorithms for NP-complete problems. You know, like we have candidates for these things. And I think that's also valuable because, as you just mentioned yourself, feels like machine learning and AI, like things work, but we cannot prove them, right? Like, it's just, why does deep learning work so well? Oh,
Yeah.
there are many nonlinearities, they come together, you know, so it probably, that's why it works. But, you know, this doesn't really like answer the question. You cannot just grab anything complex and make it work, right?
Yeah.
But there are heuristic algorithms, and there's a point to them because, you know, if people can do machine learning and AI so well, why shouldn't we be open to heuristic algorithms as well? By heuristic, I mean non-provable. But the field like really is extremely skeptical and firm against claims, which I've liked, which is good. Like it has its own skepticism built in and self-correcting, which is an aspect I like. And then there's the experimental effort.
Yeah.
Experimental effort is extremely serious. So that's another thing that's good. Building these machines in the lab, quantum communication, etc. A lot of resources, most of our resources go into the experimental efforts of actually trying to build these things in the lab reliably. This happens at IBM, Google, IonQ, QEra, you know, Quantinium, and they're exploring different architectures, psi-quantum, different architectures from superconducting qubits, trapped ions, trapped atoms, photonic computation, etc. Different types of architectures to see, you know, it's not even clear what's going to be the ultimate architecture for quantum computing. It's such an early stage. Some of them seem better for optimization problems. Some of them seem better for just standard quantum computational things. Some of them are just faster, cleaner. We hope they may have like good scaling.
Okay. So is that the job then of a quantum researcher, is trying to figure out architecture, design, also just find problems that could fit in this space of that quantum computing could solve?
Yes, yes. So if you're an experimentalist quantum computation person, your background could be from engineering, physics, device, etc., and you might be working on, you know, building better qubits, calibrating the device in real time, being able to implement gates at an abstract level, be able to implement gates and qubits in fast and reliable ways, benchmark the device so you know how well it worked or how badly it performed. If you're a theorist, you could be various things. You could be somebody who works on quantum algorithms, which means, you know, think really hard, try to come up with something that a quantum computer would be good at, or prove why a quantum computer would not be good at something. You could be working on the complexity of it, which is, if a quantum computer is good at it, how good, how much better will it be? And this would be like involving like making a proof, like actually writing a rigorous proof. You could be working on other types of quantum applications, like quantum games, you know, in particular, quantum communicational advantages, things you can do quantumly using, you know, features of quantum mechanics that you cannot do classically. You could be working on the quantum physics of things, which means like, you know, can you do quantum demonstrations on a quantum computer and finally measure, you know, that magnetic moment that's been open for years? People are like, is it one or is it two? But maybe, you know, on a quantum device, you can do it and finally answer the question.
Okay. Very interesting.
Yeah, and there's also a type of quantum advantages that called OKIP, because they're only quantumly possible. So it's not just about like doing things faster or better, but you just do not have them classically. Like entanglement was one of them. Entanglement is a feature, but it's not really an advantage. But there are things you can only do quantumly that just you cannot do classically. And I think that's interesting and less explored than it deserves to be. So that's an area I've gotten very into.
Okay.
So a little bit about, and I'm coming to some kind of an end very soon. So quantum advantage in finance and beyond. So there are quantum advantages we talked about. There's computational, and then there's beyond computation. There's the quantum threat, which is like as the quantum computers are scaling fast with this like awesome investment from government and industrial sector. So our current cryptography is going to be threatened because Shor's factoring algorithm will break the crypto systems. And actually, a corollary, because it does discrete log, the Bitcoin wallets will be in danger. So this calls for the so-called post-quantum cryptography. So if you're interested, I organized a co-organized tri-semester program on post-quantum crypto at IHP in Paris. And the talks are online, so anybody can watch them.
Okay. I'll link them as well in the description of the video here, so people can just follow the links.
Great. Some of the areas I've worked on that touch quantum finance, you might call, advantages in finance is quantum supremacy for random circuits. So this is what like Google made a splash on in 2019, and it's been going on. These are references. It's Nature Physics paper and Fox paper that I did with my Japanese colleagues. And if you like, expository articles, there are these couple, and I blogged about it at some point. Around 2018, I got very interested in quantum advantages in a wider sense, so beyond just computational time. And they have applications in communication, complexity, and cryptography. Like, for example, security, blockchain, and finance can benefit from. And it's very nascent. Like, it's a lot needs to be done in this area. And I think it's promising. It would be interesting to investigate in the next few years. So quantum supremacy was the previous slide I told you about. And there are other things. So we further developed it while I was at Google, certified random number generation, randomness extractions. So you can use like output of a quantum circuit because we know it's more random than you can classically get.
Yeah.
You see, classically on a classical computer, if you want to get randomness, at the end of the day, it's kind of like pseudo-random. Every algorithm is kind of pseudo-random. They're great. I mean, they're great pseudo-randomness. There may be actually no point in doing better than that. But at the end of the day, it's pseudo-random. But, if you look at actual output of a quantum device, it's at a fundamental physics level, non-deterministic and probabilistic. So you're getting a randomness that's beyond an algorithm.
And that is a huge advantage in finance because I don't know how many people focus on this, but even in grad school, we focused a lot on that concept. We spent I think it was like 2 days talking about like how do you generate a random number?
Yeah.
And we start to learn like about IBM, I think is the one that we currently use most computer applications, but it's not technically random. And in finance, right, we're modeling people and people are actually random. Like there's a lot of things that seem logical and then there's a lot of irrational behavior, or at least it seems irrational. And I think for finance, having something more random or actually truly random would be a large breakthrough in a lot of the simulations that we do because the computational speed or the dynamics behind some of the problems we're trying to solve.
Fascinating. Yes. And then you can extract them exactly like you said. So, that's a whole field, and exploring its applications is not fully, I wouldn't say it's fully resolved. There are interesting things to be said and done. So maybe we can talk more even. If you've read Satoshi's original paper, in it you see Merkle trees. Merkle trees are ways to like commit to bit strings. It's called bit commitment schemes with many applications. At the time, a student of mine who is now brilliant. He's brilliant and is now faculty at Berkeley. We came up with quantum Merkle trees. So it's a way to commit to quantum states the same way and with efficient verification. More recently, I've done some work on quantum function secret sharing, which, like the overall picture is that suppose you're a hedge fund and you want to do a quantum computation. You don't have a quantum computer, but, your algorithm wants to do a quantum computation. Well, what can you do? Well, you can delegate the computation to somebody who has a quantum computer. Maybe, you go through cloud, you connect to IBM's device and run it. But you don't want to expose your computation. You're a hedge fund, it's proprietary information. So how can you hide your circuit? So this is a work we did called function secret sharing, but think of a function as like what you want to calculate. So there is a way you can send random circuits or random looking circuits, and from the answers from the quantum computer, you can piece together the answer to the actual computation you want it to do.
Okay.
So like, as far as they can tell, it's like a random, useless thing, but for you, it's very meaningful. It answers your question.
Okay. That
Or
makes
more
sense.
recently, yeah, or more recently, in this paper published in Crypto, um, with Sam Gunn, who was an intern at Google, we did quantum one-time programs. So if you have Gen AI, these are non-deterministic functions, actually. Like if you ask ChatGPT a question twice, you get slightly different answers. So it's not like deterministic. Um, and there are questions like, if you're a hedge fund, you want to ask a question from, say, ChatGPT. There are a couple of things you don't want to do. One is like expose your prompt because they get to see what you're asking. Second is that you may not want to deal with the latency, like send the question, wait for the answer. And from ChatGPT's perspective, they want to sell you tokens because you're a hedge fund and they want to make money. How can you do this securely? So like they send you pay them money, the hedge fund pays them money, they send, I don't know, like 100 tokens for 100 prompts you can run. Then you run the prompts locally, securely, and it can be certified that you only ran 100 times, not more. So ChatGPT is happy, they sold you tokens, you cannot do piracy, you cannot copy the tokens. This is one application of quantum that I'm very excited about, is non-cloning. You cannot actually, unlike classically, you can always do Xerox machines and printing and take a picture of things. But quantumly, you cannot copy unknown states with high fidelity. That's
Okay.
actually a theorem, mathematical theorem. It's called non-cloning principle. So that can be used here to make sure that the tokens are used up per prompt, and everybody can certify it rigorously. I think this is a good place to stop maybe and talk more one-on-one or just answer questions. It's just like a overview of the field and where it goes, where it ends for finance currently, and there's a lot more to be done. Exciting
Yeah.
future ahead.
So one of the areas I've been looking or thinking more about is with LLMs, it seems like they're hitting a power consumption problem. And of
Mm-hmm.
course, I think a lot of people are heads in the cloud, things will magically just resolve. But I feel like there has to be some sort of quantum application where it's like the computation on can be streamlined so to a point that quantum could be a solution to actually reduce the consumption of energy for LLMs. Do you think that's
Yeah.
even a plausible solution, or is there any sort of, I mean, obviously it would require research and applications and everything,
Mm-hmm.
but do you think that's a feasible idea, or is that for some reason just a dream?
It is a feasible idea, and people do discuss this. Like I've heard it recently come up a lot, but I don't think we have a general purpose solution yet using quantum to like overcome computational, um, you know, the expensive compute that's needed for power consumption. But a type of quantum advantage could indeed be like power usage.
Yeah.
Um, so
Where
yeah, people talk about it, but I don't believe we like have very settled answers on it.
do you feel like it's underfunded? I'm often curious on that point of like, I feel like end up on these like very hype trains of like something comes up, like string theory is one of these. So I read my science for free time. Like string theory comes up and it seems like we abandon everything but string theory and we chase it for a while. And now LLMs is like the new thing. So everyone's chasing, LLMs and all the investments going towards that. And then all of a sudden it's like I feel like quantum's there, but it doesn't seem like it's gotten really that popularity. Do you feel like
Hmm.
we're misallocating funds on that? I know government funding in general has fallen off over the last 50, 60 years.
Yeah, that's an interesting question. I mean, from a private sector, it is what it is. People like VCs, they fund hype.
Yeah.
They just fund hype. That's how it is. From a government perspective, US, when US gets into things, things happen, which is a good feature. Like, so quantum computing has been funded to the extent that it would be funded in Canada for a long time. So Canada was very early in embracing quantum technologies, decades, I would say, at the scale that it can do, and European Union also, like it was very early on, recognized quantum. But the US got into it and things have really transformed, which is great, but it was a little late.
Okay.
I think a bottleneck sometimes it might be it was a little later. It's not late in terms of like uh, losing or something. It was just later to embrace. So people went to Congress, got quantum leap approved, and so forth. I think maybe inefficiencies in policy making are more of a bottleneck than actual the dollar amount. The funding for quantum has increased a lot in recent years, which is good. Um, Relative to AI, of course, is not so well funded, but it's much better than when it was like when I was a student. When I was a student, there were, like I was very academic at the time. There were times that were just like no openings in quantum, like you just had all these good papers. There's like nothing really out there as a faculty position or something. So anything remotely you'd be excited about. But things have really changed. Um, and to some extent, it's also understandable because quantum computing and quantum technologies, quantum computing especially, remains a bit speculative. Like we don't have a real demonstration that you would say, "Oh, okay, this is of commercial value," and look, we cannot do it classically. So there's a bit of skepticism towards it. Not always very well informed. So, but there's like quite a bit of industrial funding, which is good. Like people are getting into it. Government is funding it more. It's hard for me to tell whether how adequate or inadequate it is right now. But I think there's also a smartness to money. Like as soon as we find some commercial things, I think people will be quick at allocating resources.
Okay. Where do you see quantum computing sitting in like 5 to 10 years?
That's an excellent question. I think it's going to be a very exciting time in the next 5 years. It's hard to predict or say anything that's like remotely non-random for like horizons of 10 years and above. But I think the next 5 years, these quantum computers are going to be scaled to a point that we can at least start claiming quantum advantages, even if we cannot prove it. But we can say, hey, look, this is a hard thing to simulate that we just did. I think in the next 5 years, the quantum threat has to be taken very serious. So I'm involved in a startup that's working on this. So we have to really think very seriously about in migrating, to new crypto systems that are beyond what we have now because they're going to be broken. And there's of course always this thought that maybe NSA or China, etc., they already have broken it, and we can really get into that. But as far as we can tell, publicly available quantum computers are not there yet to break these things. But they will soon.
Yeah.
So that's a very serious thing that has to be taken up in the next 5 years. Quantum communicational advantages like quantum finance, I think, would be very exciting in the next few years, just to like really flesh out what can be done there. Because it involves more than just computation. It could involve all sorts of things that has to be carefully examined.
Okay. That makes
It's a
sense.
great time. Another area is quantum AI, which is very fascinating. Like AI has been great at helping quantum. Like like AI is good at learning the noise model
Hmm.
for the quantum device and then do error correction, help you do the error correction better. That's like a great thing you can do. But the other way around is the hope. Like you can come with quantum and do things that AI wants to do much faster, or like you said, with like less energy requirements, etc. This is a hope. There are like some academic suggestions, but it's been like one of those interesting open problems. What can you do for AI using quantum? Yeah.
I think also one of the hardest areas, which I think a lot of people aren't focusing on, is it's hard to frame things into a quantum framework. And I think it's a really interesting area, especially in like the finance space of like even myself when I started, I think of everything very traditionally. That's how everything operates.
Mhm.
Everything's deterministic, traditional. It has to follow these steps. But I ran into an individual, worked at some company in Canada that works for one of these quantum companies at an AI conference, and he was talking about his work is just trying to reframe other problems into a quantum framework. And I
Right.
think that's a lot of like where finance, where I think it's like we need to start looking for problems that could be solved by quantum, methods, quantum
Mhm.
computation. And then
Mhm.
it's like then we're gonna have to lean on, more of the quantum scientists of like, hey, I've got this idea. Like, can you help figure out if we can get these things kind of as a team across the finish line?
Yeah, this is actually an interesting point. Unlike AI, the entry barrier to quantum computing is fairly high technically. It's just like even at the very beginning, the foundations of it. To begin with, you have to deal with complex numbers, which is like is not the biggest problem for someone wanting to get into quantum computing. But just to tell you, like you have to start thinking in terms of complex numbers, and it's counterintuitive conceptually certain things, and also mathematically, it is just much more involved than say AI and ML. So that makes the translation a little bit harder and also frustrating for some of the practitioners because like people can get excited. Oh, quantum is random. Maybe we can make casinos and make a lot of money. And yes, sounds great. Yes, yes, we see. I see why you would think that, but like to really bridge the chasm is or chasm is not so easy to do in a meaningful way.
Yeah, definitely. For one final question, for anyone who's interested in quantum computing or quantum topics in general, how would you recommend they go about that process? Is there like a specific, I guess we'll start as a degree. Let's look at a student. If it's a student, is there a specific degree you think better prepares you for that? Or is there some sort of combination of degrees that you would look at to kind of get into that space?
So if you want to get into quantum computing as a student and you've chosen a school, I think the best way to go about is that quantum computing can be done in physics, in math, in engineering. It can be done all sorts of places. But the way to decide if you really, really want to do quantum computing, let's say that is the case. You then ask me whether somebody should get into quantum computing. So let's say they want to do quantum computing. I think the way to do it is to see who in the faculty are involved in quantum computing, what are the quantum initiatives, quantum centers, and what are the big participants, and choose accordingly. Like you can work with people and take their classes. That is the best way to learn about quantum computing. Not so much, and you learn what you need on the way. It isn't so much like a degree. I am a counterexample to this. I always try to stay close to foundations because I thought it would give me uh, mobility and versatility to like move into different fields. That also works. And it is good because you can move across fields, which I've done many times, and it's good. But it comes at a cost because you have to spend the time, energy, and you got to really be passionate about understanding things at a fundamental level, etc.
I think it's a hard decision to make as well. I've always
Yeah,
in many ways, I've been like this floating across multiple disciplines. I didn't have like a really nice linear path of like, getting the exact degrees to line up with it. Uh,
right.
but I do feel the pain often of trying to get some sort of transition and then fall into that track and fit in with the crowd, I guess, in many ways. So,
Yes, yes, that's right. That's right. Well, it's also if you make it work, usually it's going to be very interesting and exciting and inspiring. But it's harder to make it work because, like you said, you're not with a herd.
yeah, yeah, exactly.
Can I add one other thing, Dimitri, since for people interested, there are a lot of good online resources. For more technical, I mean, there are good books. There are some, reference books you can read, blogs and stuff. One set of video lectures I like is what IBM put out. It's technical. It's more on the technical mathematical side of things. Um, by John Waterhouse on Qiskit. So that's a good set of lectures. John Preskill of CalTech has some good lectures online. I believe MIT has also put some of their lectures online on quantum computing that may be visible on OpenCourseWare. So I guess a general trend is like if the person presenting is really knows what they're talking about, so like is one of the good scientists in the field, and they have good viewer base, that chances are the lectures are gonna be, of course, technically good, so you won't be misled conceptually, but also well presented. And I have a blog if you want to see some like technical things.
Yeah, we'll link them below as well. I'll link some of those, your blog and a few of the other resources so people can kind of dive into that.
This was a lot of fun.
Yeah, thanks for coming on.
Yeah, thank you. All the best.